So what is distance? So how did this distance thingy start? Well, it started, I think, a lot with surveying. They surveyed the land in the days of old, 3,000, 4,000 years, even before Christ. They were building these structures, these buildings, pyramids, all kinds of buildings. And, the architects or the people who eventually got the hang of it, they had to measure the land. And so one of the issues was is that they weren't concerned with physics, with a distance of physics. Like distance of physics is just separation. That's it. That's all Mother Nature understands. She doesn't understand 1 meter, 1 foot, 1 inch. She doesn't understand any of that. She only understands separation. That she understands. And this is not what these people did. They had to measure the land. They had to have, so many feet, so many inches, and so on. And they had their own measurements, obviously their own units. But they had to measure to find out how much. And that's how, this distance thingy entered into the world of math and really into the world of geometry. Okay. And so here you have an example of that. Okay. Uh, what was geometry all about? How did it start? Well, it started with land measurement. That's what geometry means. Geo, land, and metry, measurement. That's what it is. It's land measurement. What were they measuring? Were they measuring time? Were they measuring motion? They were measuring distance, but not distance of physics. They were measuring distance traveled. Traveled by whom? By the end of your measuring tape or whatever they use to measure the distance. So they were looking at units. How many units is it from here to there? That's what they were concerned about. And they started doing some math, some rudimentary math, and they eventually developed, a lot of this arithmetic first and math and all this other stuff. That went hand in hand with so-called geometry, measurement of the land. Why? Because they're going to measure. They're going to get numbers. They're going to get units. Okay. So the earliest records, beginnings of geometry, can be traced to ancient Mesopotamia and Egypt in the second millennium BC, and I'm sure even before then. I'm almost sure that you go 3,000, maybe even 4,000 years ago, you would have measurements. And these people are the only ones that maybe started documenting a lot of that. Okay? Early geometry was a collection of empirically discovered principles concerning what? Lengths. Was it length? No, it was distance traveled. That's what they call length. They're unrolling the measuring tape to measure the length of the table. What are they measuring? Distance traveled, not length. Okay, so length is just continuous matter from one edge to the other. That's what length is. But when you put some numbers and units to it, now you're talking about something else. Okay, so that's what it is, measurement. Okay, angles, areas, and volume, which were developed to meet some practical need in surveying. Yeah, it was a practical, meaning they were talking about technology, not about science. Okay, they were talking about we got to do something, we got to build something, we got to make it practical. It's got to have some use, and that's got nothing to do with science. Science is about discovering how Mother Nature runs her shop. That's what science is about. This is technology. Okay, construction, astronomy, and various crafts. That's what it is. It's what we call technology. So that's how it all started, and that's how science got mixed up with technology and mathematics with geometry, meaning physics with geometry because they fit geometry within physics. Okay? So if you ask someone where does geometry belong today, they say it's within physics. Well, not that geometry, not the measurement, not the values and units. That has nothing to do with science or with physics. Okay, and here we have good old Mr. Plato, and he said, "No, let no one ignorant of geometry enter here." His academy, and so geometry had developed to a point where these people considered it, holy almost. They said, "No, no, anyone who knows geometry, he's an educated person. Everybody else is a peasant. Go work in the fields, fellow." Okay, so only educated people would enter there, and what did they have to know? They had to know geometry. What was geometry? Well, it was working with units and numbers. Okay. And here's an example of that. Okay, these are the units that the Greeks had. Okay, what were they? Well, they call them units of length or units of distance. No, neither. What it is, what you're staring at is distance traveled. Distance traveled by what? By the end of your measuring tape. You're unrolling the measuring tape and measuring how many feet from origin the tip of your tape unrolled. Okay, and these were their units. These were the small units. They also had big units. Okay, for like the mile and so on. I didn't put this in here, but you get the idea. The idea is that they created numbers on the one hand, which was the arithmetic, the beginnings of mathematics, and you had on the other one, on the other side, the units. They put them together, and they had a numbering system followed by units that they used to measure what? Distance traveled. Distance traveled by the end of your measuring tape from its starting point. That's what it was all about. It still is to this day. Nothing has changed. Okay. And so because of that, a lot of these Greeks were involved in analyzing distance because they were trying to find out something about motion. And you had, like I talked about a couple of weeks ago, you had the Parmenides. They were known as the Eleatics, and you had Zeno, who also vouched for Parmenides. And what they developed was all these paradoxes to show you that there is no motion in the universe. Why? Because you have not moved the distance. You have not changed distance. Okay, and here's Zeno. Okay, he says. This is out of the Wikipedia. Okay, for motion to occur, an object must change the position which it occupies. Okay, yeah, you have to have two or more locations. In any one durationless instant of time, suddenly, not only do you have motion introduced, you have time introduced, okay, into the discussion about what? Distance. Why should you introduce time or motion in distance if distance is just separation between two objects in physics? Well, the only reason is that you're not going to talk about distance, you're going to be talking about distance traveled, and that's when you have to talk about motion and time. That's how time enters the discussion of distance, meaning distance traveled. Okay, let's keep that in mind. The arrow is neither moving to where it is, nor to where it is not. This is the reasoning, okay, that they had. It cannot move to where it is not because no time elapses for it to move there. Okay, it's not there yet. Okay, it's not the future. It cannot move to where it is because it is already there. So no time has gone by. Again, all related to time, this distance traveled. Okay? At every instant of time, there is no motion occurring. If everything is motionless at every instant of time, and time is entirely composed of instants, then motion is impossible. This is how they concluded that there was no such thing as motion, the Eleatics. Okay? And of course, the atomists, as I discussed the other day, they had a different idea. They said, look, motion is a reality. You're not going to tell me there's no motion. Here, I'll move my hand to prove it. So don't tell me there is no motion in the universe, that it's an illusion, that it's illusory. No, there is motion. And we're not even going to talk to you guys because if you're going to go to that level, well, then we have no discussion at all. That's more or less the way they handled it. And here's another paradox involving distance, and it's the famous Achilles and the tortoise. Okay, and here we have Zeno again. And as the competitors start running at the same constant speed. So they're running at a constant speed, okay? But Achilles is faster than the tortoise again, okay? So very clear, right? Tortoise runs slower than Achilles, okay? So after some finite time, Achilles will have run 100 meters, bringing him to the tortoise starting point. During this time, the tortoise has run 2 meters, okay? So Achilles runs 100 meters, and he's now where the starting point of the tortoise was. And by that time, the tortoise moved 2 meters. So the tortoise is still ahead, okay? And it looks like, Achilles is just going to catch up with him because he's running at a constant rate, but he's always has to reach the point where the turtle left. Okay, so every time he reaches, the turtle moves a little more. And every time he reaches, the turtle moves a little more, and he never catches up with the turtle. That was the idea. That was the reasoning. And so again, with it, they showed that there is really no motion. Okay, that there is no change and that it's illusory. Okay, and so it says whenever Achilles arrives somewhere, the turtle has been there. He still has some distance to go before he can even reach the turtle. Okay, so he never catches up with him. And so yeah, Greeks played around with it. The people who had nothing to do, they played around with all these concepts and they tried to figure out whether there was motion in the universe. Meaning, if there's no motion. And I don't know how they didn't think that if there's no motion, there could be time because they were talking about time, but not about motion. But they said there's no motion, but they still talked about time. So what is time then? You got to define it. And this was also, again, related to distance, really distance traveled. Okay. And here's Aristotle. He takes on the subject. Okay. He does analyze Zeno and also the atomists. And so he's given credit for this. I'm sure it existed. The idea was there before him. Okay, and it's the wheel paradox. And it's here is summarized: nested wheels sharing the same center. Okay, so you have a wheel. You have the spokes maybe, and you have a small wheel and a big wheel. Okay, and same distance traveled by both circles in one revolution. So if the big wheel makes one revolution, the other guy reaches the same distance, but it's a smaller wheel, smaller circumference. Okay, smaller radius, smaller circle. Distance traveled by the larger circle is equal to its circumference. Distance traveled by the smaller circle is greater than its circumference. Okay, so there's a little paradox in there. And again, they're talking about distance, what? Travel, not about distance. Okay, so irrespective of the conclusions or the reasoning behind it or the explanation they gave, we don't care about that. I'm just saying here that all these people talked about distance traveled. not about distance, not about separation. I want to keep that completely in mind. It's going to be important. Okay. Okay. Here we have a couple of centuries later. In fact, a few more. Mr. Galileo Galilei. And what does he say? Well, he's the guy who allegedly threw two rocks from the Tower of Pisa, which I think never happened. Okay. And I discussed that in the past. Okay. It was someone else who threw the rocks and from in Holland, not in Italy. Okay, anyways, the distance traveled by the falling body is directly proportional to the square of the time it takes to fall. That was his conclusion. I think he did it with rolling balls, rolling down an inclined plane. He timed those, and that's how he reached that conclusion. But what was he talking about? Distance traveled. It wasn't about distance. What is the separation between the tower, top of the tower, and the bottom of the tower? He wasn't concerned about that. What was the distance between on his inclined plane between the top and the bottom? He wasn't concerned about that. He wanted to know what is the distance it traveled. The balls traveled, right? Okay, so it was all about distance travel. I want to make sure everybody understands that. It wasn't about distance, the distance of physics, separation. Okay, and a little later we have this fellow, and his name is Newton, and he wrote in his book, in his Principia, I say that a corpuscle put in place outside the surface of the sphere is attracted to the center of the sphere by a force inversely proportional to the square of its distance from the same center. Okay, so what was he explaining? He was trying to explain gravity. Okay, but again, he's talking about, the motion of something towards something else. He's saying, what is the force of attraction? What is force? Well, force is apparently something that's moving. Okay, so he was talking about in some measure, he was talking about distance traveled. Okay, and then he continues, if the attraction of a body by another shall be far greater when it is attracted in contact than when the bodies may be separated by the smallest distance from each other, then the force of the attracting particles in the distant parts of the attracting body decrease in a ratio greater than the square of the distances from the particles. Okay. What's the problem with Newton? Well, the problem is that he did not realize that little distance there squared that he's got at the bottom left there, force equals gravity mass over distance squared, that distance is not distance traveled. That distance is separation between the two masses, m1 and m2. Okay, and I think this was a big failure that even persists to this day. Okay, so let me show you here my take on this. Okay, that's where I'm going to get to. Okay, here you have the distance traveled of force equals mass times acceleration, which is Newton's second law at the upper left. Okay, that's distance traveled because it's part of acceleration. The tension, which I put there, which they put as force equals g mass over distance squared, it's tension. There is no motion there. It's only separation between the two masses. Okay, so force equals mass times acceleration, Newton's second law, does not equal Newton's gravitational law. Okay, we're going to talk about laws. One does not equal the other because one has distance traveled and the other one has distance. And there on the right, I'm showing what the differences between these are. In the case of the gravitational equation, distance is static. There's a separation, okay? And that separation we call distance. For every value that you get in the gravitational equation, you have a static distance. You can add them up and then you have motion. But until you do that, all you have is for every value you have just distance. That's not the case in the force equals mass times acceleration, Newton's second law. There the distance is dynamic. The distance in the gravitational law is between two objects. The distance is traveled by one object in the second law. Then each frame in the movie picks a static distance. That's in Newton's gravitational equation. That's not the case in the second law, which each frame in the movie is a cross-section of the itinerary of one object. Okay, so we're talking about two objects versus one object in all cases. Number 4 there, distance decreases when acceleration increases. And that's not the case. The opposite is true for the force second law equation. Distance is towards the other object in the case of the gravitational law. That's not the case for distance in the Newton's second law. Distance traveled is away from an unspecified object, typically the origin of that object, single object that is moving. The distance is a measure of weight in the case of the distance in the gravitational equation. Distance is a measure of velocity in the case of Newton's second law. And finally, the force increases when distance decreases in the gravitational equation. Force increases when distance increases in the second law. So you can see there are differences in these distances, first of all, and it's because they always use distance traveled that they never discovered the differences between these qualitative differences between these distances. That's where the problem was. Okay? And to this day, no one has discovered it. And it only got worse at the turn of the century, 19th to the 20th century, right? You have Mr. Einstein come in there, and really it wasn't him. It was people who came before him. I discussed that a couple of weeks ago as well. But here it is. We have the length contraction, which is the distance contraction, which is the distance traveled contraction, because they're talking about a distance traveled. And there you have the example. You have the observer dilation, the passenger dilation. What are we talking about? Well, if you have a train and lightning hits the front and the back at the same time, according to Mother Nature, right? The observer on the train is going to see something different. Not what Mother Nature did, but what he sees, what he experiences. Since he's traveling in the direction of where the lightning struck the front of the train, he's going in that direction. The light is going to hit him from the front of the train faster than it's going to be from the back of the train. Okay, and because of that, he says, no, the lightning struck first in the front of the train, later on the other one in the back. On the other hand, a passenger the observer who's on the station, just watching that, he should receive the signal right in the center of where between the front and back of the train. If lightning hits at the same time, he's going to receive those two signals simultaneously. Okay, so what all these people were saying at the turn of the century is that these guys are going to measure distance traveled by light and by everything, right? They're going to measure it differently depending on whether they're in motion or not, especially if they're moving close to the speed of light. And so they talked about what? Length contraction. That's scary stuff. You've got length contraction. The length, the distance traveled contracts. Man, that's deep. Okay? And then you measure, this is a summary of essentially what it stands for. You measure different distance traveled, right, from different reference frames. That's what it amounts to. Okay, and the reference frames has to do a lot with how fast you're moving, et cetera, et cetera. So it's got to do, again, with distance traveled and not with distance, and that's why they got into all this mathematical gibberish where they say, oh, distance gets shrunk, meaning, the length of an object gets shrunk because the distance it traveled gets shrunk. Well, are we talking about distance traveled or about length? What are we talking about? Are they the same? Are they the same from a physical, from the point of view of physics? That's the question I'm asking, okay? And so here's I got another one here. I missed one. Okay, anyways, here's the definition we have today. The distance, for distance, right? Distance, a numerical measurement of how far apart objects or points are. That's the definition you find, okay? And in mathematics, in everyday physics, right, or everyday usage, right, distance may refer to physical length. No, not in science. Length is not distance, okay? And I like to synthesize it the way I say it there. Distance is what lies between lengths, okay? Length is what an object has. Distance is what is between two objects, okay? And so to confuse the absence of an object with an object, we have a little bit of problem, because distance is related to space, or is to space what length is to an object. These are two properties that should be separated. You should not confuse them. They're not synonyms, okay? And so you look up the word length. This is a measure of distance. So we have a circle. What is distance? Well, it's a measure of length. What is length? It's a measure of distance. Great. We learned a lot. That's all we have today. And it says in the International System of Quantities, length is a quantity, not the continuous matter from edge to edge of an object, but it's the length is a quantity with dimension distance, whatever that means. Dimension distance, meaning meters, or inches or whatever. So again, these people are rolling the measuring tape, and because they're rolling the measuring tape, they're measuring distance traveled. And because they have always dealt with distance traveled and never at all with separation, with physical separation, they never discovered that Newton's law, universal law of gravitation, as it's called, deals with separation and not with distance traveled. Whereas the force law, second law, deals with distance traveled. And so we have separation versus distance traveled. They're not qualitatively the same. And if they're not the same, we have to look at it from a physics point of view and find out how they relate to each other. And what I have done in the past, and might do it again sometime in the future, is shown that it's got to do with this principle of equivalence. Okay? It's related to that, which I'm not going to deal with today.